Kia ora tātou. My name is John Hosking. I'm the Dean of Science here at the University of Auckland. It's my very great pleasure to welcome you to the inaugural lecture of the Ihaka Lecture Series. This series is named in honour of Ross Ihaka, sitting here. Ross, of course, is one of the co-founders, along with Robert Gentleman, of the statistical programming environment R. Both were here in the Department of Statistics when they decided to build some experimental software back in 1991-92, so a wee while ago now. One of the key decisions that they made was that it was to be free software that's free to download and freely modifiable. And this has been one of the reasons for its extraordinary success. And that success is extraordinary. By standard academic standards, the paper that Ross and Robert wrote has attracted nearly 9,000 citations. I wish I had a paper like that. But its real impact, R's real impact, is the number of users worldwide that make use of R. So that's estimated in 2014 to be over 2 million. I'm sure it's grown considerably since then. R is now ranked 5th in the top programming languages, behind C, Java, Python and C++, but ahead of languages like C# and other academic programming environments such as MATLAB and domain-specific languages in the stats area such as SAS. This is almost a textbook example of curiosity, inventiveness, great ideas and sharing and openness leading to good science, great science. Ross, through R, has had a profound impact on the practice of modern statistics. In 2008, Ross was awarded the Pickering Medal from the Royal Society of New Zealand in recognition of his achievement. He has a rock star status amongst statisticians, but as anyone who knows Ross knows, he remains extraordinarily modest about his achievements. When asked about his work, he said simply, "I had fun." And he finds the accolades he's received kind of embarrassing. So Ross, embarrassment aside, this is a great occasion to celebrate the impact that you've had as an academic, and I think this is a very fitting series to commemorate that. So it's a very great pleasure to open this lecture series to be held annually in Ross's honour. Thank you.
So good evening, my name's James Curran, I'm a professor here in the Statistics Department, and let me say at the outset that it's just absolutely fantastic to see so many people prepared to give up their Wednesday night to come along and listen to a statistician. Who would have believed it? We have a fantastic lineup for you over the next 4 weeks, and tonight we're going to start with one of the best. So in some sense, Dr. Hadley Wickham needs no introduction, but I did promise him that I would embarrass him. So we'll start out with a brief one. So Hadley is actually a former graduate of our department. After graduating with a master's degree from here, he went away to Ohio State and got a PhD. Some people might say that he actually rewrote the field of statistical graphics. He then went on to a position at Rice University in Texas, and then was snatched up by RStudio, which is a product I'm sure most of you are familiar with. John used the word rock star to describe Ross earlier, and perhaps the same can be used for Hadley. So I remember seeing a talk with the academic Peter Donnelly telling a joke about how can you tell the difference between an introverted and an extroverted statistician, and the extrovert is the one that looks at somebody else's shoes. But I think we can take the metaphor or the rock star thing just sort of one step further for Hadley. So I don't know if you can all see this, but when you meet somebody and you don't have a piece of paper, you ask for something to be signed. I'll never wash my laptop again. So jokes aside, it's hard to overstate the impact that Hadley has had, especially in the R world. And just as evidence of that, this is from an article called The Hitchhiker's Guide to the Hadleyverse. Hadley is far too modest a person to use the word Hadleyverse, and I believe last year he suggested at USAR that we should use the word tidyverse. These are, I believe, in the order of 55 packages. That was in August 2015 that Hadley has authored. They are packages that are shaping our field and are shaping the field of data science, which is extraordinarily important to us. So without much further ado, could you please join me in bidding Hadley a warm welcome, and I'll hand the floor over to him.
Thanks, James. So what I wanted to do today is to talk about some of the things that I've been spending a lot of time thinking about lately around the kind of theme of how can you most easily and naturally express yourself in R. And to this end, my goal as a tool builder is to engineer something I like to think of as a pit of success. Now, this is not a pinnacle of success, right? Because to reach a pinnacle, you have to strive. You have to work really hard. The goal of a pit of success is you kind of almost like fall into it without even trying. So certainly I think we're a long way from just falling into success in R. But today I wanted to sort of think about to talk about some of the things that I think make coding in R lead you to fall into this pit of success. And really, in some respect, I think the thing that helps you fall into this pit of success is theory and some kind of consistent principles. So these are things that normally you wouldn't learn. I don't think you need to learn them early on in your journey as a data scientist in R, but they're things that you will kind of notice, you'll discover naturally. And because there is this sort of rich underlying theory, my hope is that my success, to me, is when you try something that you didn't know if it would work or not, and it just works. So today I'm going to talk about kind of a general strategy for solving problems that I think is really useful, and how we can see that reflected in R. So basically, I'm going to argue that a really good way of solving complex problems is to break them up into simple pieces, combine them together, and hopefully those simple pieces will also have a consistent structure. So I think there's two main reasons that solving complex problems with simple pieces is really important. The first one is iteration. So whenever you do a data analysis, whenever you do a visualization, whenever you do some data manipulation, almost always the first thing that you do is wrong. And often the second thing that you do is wrong as well, and the third thing is wrong as well, and the fourth thing might be wrong. And I'm someone who's been programming in R for like 15 years now, something scary. But this still happens to me all the time. It's not like I start typing R code and it works right away. Instead, what I've tried to engineer is a workflow where I can fail as quickly as possible. And that's why this idea of simple pieces is so important, because you can take a little step and check your work. And if you haven't gone in the right direction, you can just take a step back. If you kind of take a long wandering journey and like 2 days later you discover, oh, I'm not actually where I want to be, you've got a long way to backtrack. You've wasted a lot of work. So if you can break up a complex problem into simple steps and check your result, check your work after each step, this is a really good way of solving complex problems. The other thing that I think is useful about these simple pieces is that not only do they allow you to solve this problem, but maybe you can rearrange those pieces in a new way to solve a new problem. So you might be familiar with the pieces, but you can rearrange them and solve a new problem that you hadn't thought about before. And so what I'm going to talk about today, I'm going to basically break those components down. We'll talk about them one by one as how they reflect and as why they matter in R. And I'm going to start off by giving you a challenge. So here is some R code. Hopefully you're all familiar with R code. I want you to read this code. I want you to figure out what's the point of this code, and I want to see if you can spot the mistakes. So talk this over with your neighbor. You have 1 minute starting now. Okay, time's up. So does anyone want to take a stab at telling what the intent of this code is?
Any value of each of those columns that is equal to -99 you want to put as not applicable.
Right, so this is a pretty common scenario. You're reading some data in some crazy format, and missing values have been recorded as -99, and I want to convert these to R's missing values, so when I compute the mean of these values, I don't get some crazy number. So what's wrong with this code? Well, I've created this by copying and pasting. And as whenever I copy and paste, I've made a few errors. So you might have spotted this 98 here. And you might have spotted this I and J. And anything else? Well, so C and D are absent here, but that's not actually a mistake. C and D are actually character variables. So you don't know that, right? So here I've tweaked the code a little to highlight that. I've added a comment to kind of explain why they're not there, and I've highlighted my mistakes. Now, I am so bad at copying and pasting that typically when I create a slide like this where I've deliberately introduced 2 mistakes, there's normally a 3rd mistake as well. I seem to have avoided that tonight. So the problem with duplicating your code via copy and paste is, first of all, it hides the intent, right? You all as experienced R users can kind of read between the lines here and understand what's going on, but you certainly couldn't guess that C and D were character variables, so didn't need this transformation. And because I have all this duplication, I've also introduced these possibilities of error. So to me, like the piece, the thing that you use in R instead of copying and pasting is a function. So I think a great rule of thumb is it's fine to copy and paste 3 times, but as soon as you've copied and pasted more than 3 times, it's time to write a function. And so here I have written a function, and one of the great things about functions is you can give them a name. And so immediately this code is easier to read because I can now divine the intent a little bit more easily. The goal here is to fix these missing values. So the kind of unit of problem solving in R is the function. You write code, you just type out some script to solve a specific problem, one problem. A function allows you to solve a class of problems. Now, one thing I'm not going to talk about today, but one of the things that I think is really great about R as a programming language is that R is a functional programming language, and that means you can write stuff like this. Here I'm using a little function from the purr package. It's going to take a data frame. It's going to say, for every column where this is true, apply this transformation. So now once you've learned what this function does, and if you haven't ever heard of this function before, that is fine because I only wrote it like literally 3 days ago. But once you get the idea of this, right, I'm going to take an object, I'm going to see what parts of the object I want to change, and I'm going to apply that transformation. So this is a really, really powerful aspect of our programming language, and I'm not really going to talk about this at all tonight, but I encourage you to learn a little bit about functional programming if you do want to increase your skill as an R programmer. But what I wanted to talk about today is if a function is a piece, what makes a function simple? And I'd argue generally you want functions that are like Legos, not functions that are like Playmobil. Right? The argument is that not like Lego is more fun than Playmobil or Playmobil is more fun than Lego, but the neat thing about Lego is that you can recombine them in lots of ways. The use of Lego is not constrained by the inventors of Lego, unlike Playmobil, where the uses to which you can put it are much, much, much more constrained by the constructor, by its construction. So to me, I think there are two key ideas behind writing simple functions. The first idea is that you want your function to do one thing well. And the second thing is you want to be able to understand that function in isolation. You want to minimize the amount of context you need. And so to make these concrete, I'm going to talk about two aspects of each of these. So one way a function can do more than one thing is it could compute a value and have a side effect. So I'm going to talk a little bit about functions and how ideally they should either compute something, they should either give you a value back, or they should do something. They should have some side effect that affects the world in some way. And I'm going to talk a little bit about this idea of type stability. This idea that if you don't know what type of thing a function returns, it's much harder to predict how that's going to behave when you're just reading the code rather than when R is running the code. So again, I'm going to give you a challenge. Here are 7 functions from base R and some of my packages. What I want you to do, again, discuss with your neighbor which of these functions is called primarily to compute a value and which of these functions is called primarily for its side effect. Again, you've got 1 minute starting now. Okay, time's up. So let's do a quick show of hands. I kind of realized I started with a little tricky one, but who thinks mutate is called primarily for its side effect? And how many think because for computing a value? Okay, and some of you clearly don't know. This is a little bit of a tricky one. If you haven't used dplyr before, I'm going to say your homework is to go and read about it so you can at least deliberately choose not to use it. But mutate, the job of mutate is to take a data frame and add a new column that's a function of existing columns. But it doesn't actually literally modify the data frame that you give it. It gives you a new data frame with a new column. So this is a function that is called primarily because it returns a value. What about write CSV? Is this called primarily for a side effect or for its value? Right? Who knows what it returns? Well, I know, obviously, but it's called primarily because you want to save a CSV file to disk. What about print? Return a value, side effect. Right? The job of print is to display something on the screen. What about summarize? Another function from dplyr. Does it primarily compute a value or return have a side effect? Right. So summarize collapses multiple values down into one. We've got geom line, adding on a geom line. Is that a side effect or computing a value? Now that's a little tricky. So this actually does not, it's a little tricky because when you look at ggplot2, it kind of seems like the job of this is to make a plot appear. But what's actually going on behind the scenes is it is building up a plot object for you. So ggplot2 kind of follows this philosophy in a similar way. The way you create a complex plot in ggplot2 is by combining pieces, simple pieces. We'll kind of come back to ggplot2 a little bit later and why in some ways it's worse than ggplot1. What about the assignment arrow? Is this called to compute a value or to have a side effect? And what about RUnif? Compute a value or have a side effect? Thomas, do you want to? Primarily compute a value, yes. So here's just what we went through. Hopefully I did that correctly. Yes. And RUnif, however, is a little bit interesting because if RUnif did not change the state of the world in some way, every time you called it, you get the same random numbers back. Right? So there are some functions that by their very nature kind of have to do two of these things. So RUnif has to update some kind of global state, which is what allows it to give you new random numbers every single time you call it. But generally, you want your functions to do one or the other. I'm going to show you two examples of functions in base R that do both. And by and large, the functions in base R are really good. They either do one thing or the other, and it took a little bit of searching to find these two. So the first thing in base R, if you compute the summary of a linear model and you print that summary, you get a p-value for that model. But that p-value is not actually stored anywhere. If you want to extract that p-value, you cannot. That p-value is just printed, but it is computed when this object is printed. It's not stored anywhere, so you cannot get that value and use it in other ways you might be interested in. The kind of the counter example, the opposite side of this, is hist. Hist, you call it primarily to get a histogram, but it does also return a value, which you can use if you wanted to draw the histogram yourself some other way. You can kind of explicitly say to histogram, don't plot this. I just am calling you for the return value, not for your side effect. But this thing here, this is a little icky, I think. Having an argument to a function that changes its behavior in such a fundamental way, I think makes it harder to reason about your code. And this is related to this idea of type stability. And to paraphrase Forrest Gump, if you've got a type stable function, you never know what's going to, a type unstable function, you don't know what's going to come out of it. You have to have some additional context. So a type stable function, no matter what the input is, you always get the same output. A type unstable function, well, maybe sometimes it gives you a list, and other times it gives you a vector, and other times it gives you a matrix. It's harder to reason about because you have to not only know what the function is, but you have to know what the arguments to that function is. So I'm going to give you another little challenge. So here I've written a function called findVars. The idea of this is you give it a data frame and a predicate function. A predicate function is just a function that returns true or false. And it's going to use sapply, and it's going to extract these variables. So the goal of this function is to say, give me all the numeric variables in this data frame, or give me all of the factor variables in this data frame. So what I want you to do is read this code. I want you to execute this code in your head. You may get compiler errors, that's okay. I want you to try and predict what is each line of the code going to do here. And since this is the University of Auckland, I've included a line for experts only. If you can predict what this returns, I'll give you a gold star. So again, 1 minute starting now. the one, and it's the built-in one, which is kind of not important in some ways. It kind of is. Oh, that's okay. Okay, so now that you've run this code in your heads, let's run it in R and see what we get. So I didn't tell you anything about this iris data set. Maybe some of you are so intimately familiar with it you already know about it. But let's just run it and see what happens. So I'm going to say, give me all the intent here hopefully is clear. So give me all of the variables in the iris data set that are numeric. And what do I get? Well, it's a little hard to see here, so let's use str. What do I get? I get a data frame back. Now, what if I say, give me all the variables in iris that are a factor? What would you expect to get back? I'd hope you get a data frame back, right? Oh, I don't get a data frame, I just get a single factor. Now, do any experts want to guess at what this is going to do? So here, this is a little crazy, right? Here I'm indexing a data frame so it has 0 columns. So I'm going to have a data frame that has 0 columns and 150 rows. And you might be like, Hadley, I would never create a data frame like that. And if so, you're very lucky, because I always end up accidentally creating these crazy data frames. But any ideas what this is going to happen? So how many numeric columns are in this data frame? 0, right? By definition. So you would hope to get back a data frame still with 0 columns in. What happens? I get this rather uninformative error message that there's a invalid subscript type list. So what's gone wrong here? Well, there are 2 functions here that are not type stable. So the first one is sapply. So sapply is short for simplify apply. It takes each element of df and applies this function to it, and then simplifies the results into the simplest possible vector. So in this case, that's normally going to be a logical vector. But what happens if the data frame is empty? If there are no columns, then there are no logicals. Well, in fact, sapply never sees any logicals. So what sapply does in this scenario is it just returns a list. So sometimes sapply returns a list, sometimes it returns a vector, and in other cases it returns a matrix. So this doesn't make sapply bad, right? This in fact makes sapply very convenient for interactive programming, but it makes it harder to predict what it's going to do when you just read some code without knowing exactly what the values of these arguments are. Then we also have the square bracket, which if you retrieve multiple columns, returns a data frame. If you retrieve a single column, just gives you that single column. Again, this isn't bad. This is very convenient when you're doing an interactive data analysis, because often you just want to pull out that one column. You don't want a data frame with one thing in it. But as soon as you start putting these into functions and you start reading your code later on, it gets increasingly difficult to predict what's going to happen. So I think this idea of a type-stable function is very powerful because it makes the results of the code more predictable without understanding all the details. So I can rewrite this in 2 ways. First of all, I'm going to use another function from Per called map_logical. It returns a logical or it dies trying. It will never return anything other than a logical vector. And then in base R, we can say drop equals false, and that ensures that this subsetting operator always returns a data frame rather than trying to simplify into a vector if it can. So the atom of problem solving, or reproducible problem solving in R, is the function. You want to try and make your function simple in two ways. Ideally, you want to make each function do one thing well. Here I showed you one example of that, is that your functions ideally should either compute a value or have a side effect, but not both. And they should also be understandable in isolation. The less you know about the arguments to the function, and the better you can predict its output, the easier it is to understand your code. So once we have these simple pieces, how do we put them together? Well, in base R, there's two ways that you can use multiple functions to solve a problem. The first way is to assign each result of a function call to a variable. So here I'm doing a little analysis using dplyr. I'm going to take this flights data set. I'm going to group it by the destination. Then I'm going to summarize it, computing the average delay and the number of flights. Then I know that the estimate of the mean is not going to be very reliable when there's hardly any flights. So I'm only going to look at the flights with the destinations with more than 100 flights. And then I'm going to sort it in descending order of delay. Right, so here I'm solving a fairly complex problem. Give me the airports with the greatest average delay by combining these simple pieces. But what I've done here is I've been forced to kind of name every single one of these intermediate objects. And naming things is hard. So what you might be tempted to do is just say, well, I'm going to call this foo. And you've solved that problem, right? Now it's easy to come up with a silly name like this. But now you've got this problem. If you make a mistake down here, you've overridden the previous value of foo. So if you made a mistake, now you're going to go all the way back to the top and rerun all of your code till you get back down here again. So maybe what you'll do is say, well, I'll call it foo1 and then foo2 and then foo3 and foo4. And if you look at this code, you might notice I've done what I always do whenever I write code like this, and that is I've forgotten to increment the value of foo in one of my lines of code. Now, just like when I copy and paste code, whenever I write code like this, even knowing that I will make this mistake, I still make the mistake. So maybe we should just try and get rid of these intermediate names altogether. And one way to do that is to use function composition. So again, we've got exactly the same code, but I've just done this in one giant function call. And now I have to kind of read this from inside out, right? I start with flights, I group it, then I summarize it, then I filter it, and then I arrange it. So this has got rid of that intermediate variable problem, but it's introduced a new problem, namely that I have to read from right to left, which is unnatural because I have to read from left to right from all the function names. And then also the arguments of the functions end up spread quite far apart. So a third option is provided by the Magritte package in the form of this crazy looking operator called the pipe. And what the pipe does is allow you to write a sequence of function calls from left to right without any intermediate variables. The pipe is really natural when you are transforming a single object in multiple steps, like here. Take the flights data, then group it by the destination, then summarize it, then filter it, then arrange it. And I think this is really important. I think it's really important to think about the readability of your code, because every project you work on is fundamentally collaborative. Even if you're not working with any other person, you are always working with future you. And you really don't want to be in a situation where future you has no idea what past you was thinking, because past you will not respond to any emails. So I think it's really important to think about how can you structure your code so it's readable, because you're going to be the chief beneficiary of that in the future. So to kind of summarize the options, we've got assignment, which is great because you can read it from left to right. but you can't omit intermediate variables. It forces you to name everything, and naming things is hard. Then I showed you function composition, which is great because it allows you to omit intermediate variables, but you have to read it from right to left, which is unnatural. And then finally, we have the pipe, which allows you to read it from left to right and allows you to omit intermediate variables. But of course, there has to be a downside to the pipe. And basically, there are two reasons. I think there are two places you don't want to use the pipe. So the first is these allow you to omit these intermediate variables, but often you want those variables. So first of all, you might be able to give them an informative name, and that will help convey the intent of your analysis better. Or secondly, those intermediate variables might take a very long time to compute, and you don't want to recompute them all the time. The other disadvantage of the pipe is it's fundamentally a sequence. It's fundamentally best when you've got a linear sequence of transformations. There's all sorts of other kind of crazy graph structures you can create with code, with the other forms, particularly this form, but you cannot with the pipe. So I think the pipe is a really good fit for many common data analysis or data science problems because you take something and you do something to it multiple times. And I want to finish off this this talking about combining things by showing you somewhere where combining things does not work very well. Because unfortunately, ggplot2, the simple pieces in ggplot2 aren't really functions. They're functions plus. So when you create a ggplot2 plot, you have to add things together. And this is a little unnatural because if you're using dply, well, I take flights, I group it, I summarize, and I plot it. And now you've got to remember, I don't use the pipe anymore. I have to use plus. And now what happens if I want to save this plot? Well, I have to wrap that whole thing in ggsave. So unfortunately, ggplot2 was written before I kind of discovered the pipe. And so we've got this sort of awkwardness that you've got to switch between these different modes of composition. And I think that is one of the nicest things about the pipe. It's not something fundamentally new. It's just a new way of expressing something old. Whereas ggplot2 tries to come up with something new, creating plots by adding things together, and it has all these kind of awkward boundaries. Now, kind of interestingly, ggplot1, the original ggplot, did not have this problem. And so this is the equivalent code in ggplot1. And so originally it was not called ggplot1 because I did not know I would be creating ggplot2, but I've kind of brought it back to life as ggplot1. This is sort of ggplot 1.0 in some respects. So it's very, very similar. It just is basically brought back to life as an R package that will work currently, and it provides the pipe because the idea of ggplot1 was to use function composition. And at the time, I correctly realized that the assignment and wrapping styles of function composition were both kind of awkward, so I decided to create the plus. Now you could do that all with the pipe, which gives you this very nice sequence of transformations. You start with a data frame, you transform it to a plot, you do something with that plot, and then finally you save it. Another interesting connection with the pipe is to this rather weird and unloved feature of R, which is that you can assign in either direction in R. So as well as the usual assignment arrow, which assigns to the value on the right to the thing on the left, you can also use the backwards arrow, which assigns the thing on the left to the thing on the right. Now, personally, I believe this is still terrible and awful, and you should never do it. But it does seem like a very interesting idea. And then basically the reason I believe you shouldn't do it is because I think it's when you come back to the code later on, it's great to have the name of the thing up front because that's going to give you a hint to the intent. So one reason it's like the name of an object acts like a title or a heading does in a paper. It sort of alerts you what's coming up. And then I think just assignment is so important that if it's a thing on everything else gets indented a little bit, which makes it kind of subsidiary. This is the most this is the thing that this pipeline ends up doing. So you can do this, and it's kind of cool that it looks so natural, but I still think you shouldn't do that. Okay, so we talked about simple pieces, functions that do one thing well, and are easy to understand in isolation. We've talked about how to combine those with either with function calls, basically 3 styles: assignment, wrapping, or the pipe. But I want to, sort of the last thing is like, how can you make it easy for when you combine all these little function calls to get something that's easy to work with? Because sometimes I think, like, programming in R feels a little bit like this, right? The output from one function doesn't fit into the input for another function, so you're like, oh, maybe I could use this function to transform. Oh, that one didn't work. Oh, that didn't work either. Well, maybe I can just kind of put half this function, and oh, there's this other function over here that does half the problem. Oh, and now, that's so close, but it didn't work. Finally, I find the last function that combines them together, and now it works. So like each of these pieces is simple, right? You can easily understand them in isolation, but you still have this nightmarish solution to what seems like a simple problem. So I think it's important when you look at Lego, I guess since I'm in New Zealand I should be saying Legos. Legos are cool because they're not only simple, right? You can look at a Lego brick and understand it, but they're also consistent, right? You can take most Lego blocks and stack them, attach them some way to another Lego block. And that's what allows you to kind of go from these individual Lego blocks, which are very simple, to create art. Right? Lego blocks are very simple and they're uniform, but that does not constrain your creativity. In some ways, it almost enhances your creativity. So what does that mean for R functions? Well, that means you want a consistent data structure. You ideally want your functions to take the same type of data in and return the same type of data out across a broad range of problems. And I think the type of data structure that's really good at that in R is the data frame. And I think there's just one extra thing you need on the top of the data frame, and that is some convention for what do you put in the columns and what do you put in the rows. And that's basically the idea of tidy data. So if your data is tidy, you put each data set in the data frame, and then you make sure each variable is in a column. And if you do that, you'll kind of find naturally the rows become the cases. This hopefully seems like a really simple and obvious idea, but it legitimately took me like 5 years of thinking about it to figure this out. But what's great about this is it gives you this consistent data structure. If all of the functions work with this data structure, you're not constantly trying to jam the output from one function to the input of another function. Or to paraphrase Tolstoy, Hadley Tolstoy says, tidy data sets are all alike, but every messy data set is messy in its own way. So to illustrate this idea, I'm going to give you another challenge. This is some data about tuberculosis collected by the World Health Organization. What I want you to do is look at this data set and figure out what the variables are here. I'm going to give you a couple of hints. F stands for female, U stands for unknown, and 1524 stands for 15 to 24. Again, you have 1 minute starting now. What are the variables? Okay, time's up. Who wants to tell me one variable they've located? We've got gender. You picked one of the harder variables to spot. But you'll notice we've got males and females kind of spread in the column names. What other variable is up there in the column names? We've got the age range. So we've got sex and age range stored kind of somehow in the column names. What other variables do we have?
Is that a country code?
Yes, so Thomas is either a very smart and insightful gentleman, or he has heard this talk before. But I'm going to go with the former. And yes, this is indeed a 2-letter ISO abbreviation for the country code. I didn't give you much context here, right? But I told you it's the World Health Organization. So you might guess that the World Health Organization is going to store the country in some way. Here we have AD, which I believe stands for Andorra. Any other variables that are really easy to spot? None of you have said the easiest variable to spot? Yeah. Right, so we have country and year in the columns. We have gender and age spread across the column names. What else do we have? We've got whatever's measured, right? And again, you might just guess that they're all integers, right? So you might guess that this is a count. And this is the number of cases of TB for that age group, for that gender, in that country, in that year. So we've got 5 variables, but they're stored in 3 different ways. In the columns, in the column names, and in the cells themselves. So you can imagine working with this data set is going to be an exercise in frustration because you're going to need to use 3 different sets of techniques depending on which variable that you are working with. So what we could do is turn this into tidy data. As I said, tidy data has 1 variable in each column. So we have country, year, sex, age, and the number of cases. And this is going to be much easier to work with because each variable is stored in a consistent way. Now you might wonder, like, what about stuff that doesn't naturally fit into this format? And there's some tension here. There's always some tension between, do you want like a special purpose data structure that is absolutely the best data structure ever for this specific problem, or do you want some general purpose data structure or some general purpose tool? It might not be the best tool for this job, but you're already familiar with it. You already have lots of tools for working with it. So I just wanted to show one little extension of this idea called tidy text. This is a package by Julia Silger and David Robinson. And if you're interested, and you can read more about it here. But the basic idea, the basic question that this package asks is, how do you represent data that looks like this? How do you represent text data in this tidy format? And one easy way to do that is to say, well, I'm going to make each word an observation. Each word is going to be a row, and then I'm going to have variables about that word, like which book is it in, which line is it in, which chapter is it in, and what is the word itself. And the thing that's neat about this is not that this is the best possible data structure you can come up with for text. It's certainly not. The thing that's great about this is you can now deploy all of the tools you already have for working with data frames. And so it's very easy to go from data like that to plots like this, where I have joined in some information that gives me the sentiment, positive or negative, for each word. I have aggregated it by line within each book to find the average sentiment, and then I have plotted that across all of the books. So you can very easily do things like sentiment analysis, which might seem like complicated and strange, but they just fit it into a framework that you are already familiar with. Now you might wonder, well, not everything I do is like a simple thing like a logical or a number or a character. What about the complicated things like polygons or linear models? Well, it turns out that you can handle these in data frames as well, using something I call a list column. So the basic idea of a data frame in R, a data frame is a list of vectors, and each vector is the same length. That is the contract that a data frame provides in R. It turns out that one of the vectors that can live in a data frame is a list. And in R, anything can live in a list, which means anything can live inside a list column in a data frame. Now, working with these with data frames is a little tricky. There's some slightly annoying behavior with data frames that make this frustrating. So instead of using data frames, I'm going to show you a little bit of code that uses Tibbles. So Tibbles are basically a modern reimagining of the data frame. They take the stuff that time has proven to be successful and keep it, and they get rid of some of the things that time has proven to not be successful. But in brief, Tibbles are data frames that are lazy, they do as little work as possible, and they are surly. They complain a lot. Now, this seems a little counterintuitive that you would want to use something that is lazy and surly, but it turns out to be quite handy because, for example, when you try and extract a column that does not exist, Tibbles are lazy because they do not do partial name matching, and they're surly because they complain about it. And if you do succeed in extracting this variable, you'll note it as a character vector, not a factor, because Tibbles are lazy and do little work for you. They do not automatically convert character vectors to factors, which I think was absolutely the right decision at the time, but now factors tend to be more frustrating to work with than character vectors. More importantly, they also allow you to easily put lists inside Tibbles, and they have a nicer print method. So when you print these things out, you can actually see, well, one of the really nice things that Tibbles do for you is they print the type of every column, so you can instantly tell, am I working with integers or doubles? Am I working with characters or factors? And the thing that's important about Tibbles and list columns is they allow you to keep related things together no matter how complicated they are. And I wanted to show you two little examples of that. The first is the SF package by Edza Pebesma and others. SF is a successor of the SP package designed for working with spatial data in R, or simple features data. So this is what a SF data frame looks like. Basically, you'll see it has a column called geometry, which contains these complicated polygon objects. Right? A polygon is just a list of points, basically. Well, a polygon is just a list of points, but sometimes when you have a country might have a lake inside of it, and that lake might have an island inside of the lake, and inside that lake the island inside the lake there might be a little pond. So there's multi-polygons. Well, now you might not have, like Hawaii, for example, you might have multiple islands. Or New Zealand would be a more obvious example. So you can store these complicated objects in the data frame. You can work with those data frames in the same way you can work with any other data frame. In here, for example, I added a few bits and pieces to ggplot2, so you can easily work with them using the special geom, which automatically draws polygons. When you have polygons, points where you have points, lines where you have lines, and so on. Another area where I think list columns are really a beautiful fit is to cross-validation, because when you do cross-validation, you've got a whole bunch of fairly complicated objects floating around. So first of all, you've got your data that you've split into training data and test data. You fit the model to the training data, and then you make predictions based on that model and the test data, and then you summarize some model quality like the root mean squared error. And if you have a Tibble, you can just keep all of those things in a data frame together. And that's really great because often when you do a cross-validation, you'll discover, maybe 5 of the models had a really, really bad fit. And you'd like to dive in and figure out, well, what went wrong? Why is that data different? What happened with those resamples to make it different? Because you have this in a Tibble, you can easily say, filter this, give me all the models that have a bad root mean squared error, a very low root mean squared error, very high, rather. Okay, so what I have talked about today is a strategy for solving complex problems by combining simple pieces that have uniform interfaces. So the simple pieces are functions. Right? Functions are the atom of problem solving in R. And you make those simple by striving to have each function do one thing well. For example, you never want to have a function that both computes a value and has a side effect. And you want functions that can be understood easily with as little context as possible. For example, you want your functions to be type stable. You want to be able to easily predict the type of thing that they return. You combine those pieces in 3 ways. You can use assignment, you can use composition, or you can use the pipe. The pipe is something that's not built into R. It's not a new idea, right? A bunch of other tools have pipes, particularly the Linux command line, but every other functional programming language has something similar in flavor. Pipes are great because they allow you to omit intermediate variables when you don't care about them, but still read your code left to right. So you can easily read it as sort of a series of imperative statements. Take this data, then do that, then do that, then do something else. Finally, if you want to combine these simple pieces together, it is going to be easiest to do that if they have a consistent structure, if they are like Legos and they can all plug together naturally. I think the most common and useful data structure for that when you're doing data analysis or data science is the tidy data frame, where you have variables in your columns and observations or cases in the rows. If you need to store richer data structures, all is not lost. You can still use a list column inside a data frame, and you can jam whatever the heck you like inside of that. So to finish off, I'm going to show you, well, I've kind of talked about these principles. I haven't really given you any useful tools for doing data analysis or data science. So I'm going to finish off with this slide, which kind of displays my vision of the components of the data science process, some of the packages that myself and others have written to solve those problems, which is called the tidyverse, not the other verse, which I cannot say myself without sounding colossally entitled. And if you'd like to learn more about that, the best place to learn, if you want to learn how to improve your data science skills in R, my take on that is this book called R for Data Science with Garrett Grolman. You can read it online for free, or if you want to buy it, possibly the cheapest way, although I don't know if O'Reilly ships to New Zealand or not, but there is a discount code you can use on any O'Reilly book called AuthD, which will give you 40% off the book or something. Thank you.
Here that this is a public lecture, so please try not to make your questions.
Times, the way we learned things like R and S was, you could see what the existing code did, read it, and do likewise. And it seems that the pipes, while they make data analysis easier, they make that harder. Do you have any views on the sorts of trade-off between having more complicated machinery and machinery with a better user interface?
That is an interesting question. So, I don't know. I think there's almost some kind of like inevitable transformation, right? Like 20 years ago, you could buy a car and you can kind of understand enough about the internals that if it broke down, you could fix it, right? Maybe you couldn't build your own car from scratch, but you could at least kind of pull the pieces apart and see how it works. And now if you buy a car, it's like 90% computers and there's no way to fix it. So the tidyverse definitely is a little bit like that. I guess the way that I have tried to solve that problem is by, first of all, like trying to elucidate these key principles that will eventually kind of unify and underlie much of the tidyverse. So like a lot of the things I've done are like experiments. You can't like figure out what the best way to do something is without trying like 15 different ways and finding that 14 of them aren't very good. So I think like over time the goal is to kind of keep narrowing down on like a small set of underlying principles, and then to explain those principles in a way that is easy for other people to understand apart from me. So one example of that is like the tool that powers like non-standard evaluation in dplyr and other packages. I think we've finally found like the right way to express that. It's now called, you may have heard the talk about lazy eval. It's now called tidy eval. I have had, I think now, like 5 epiphanies where I'm like, oh, I finally understand non-standard evaluation. And I am now confident that I really do understand it. And I will not have any further epiphanies. But so yeah, like, so I agree, it is harder to understand. I want to try and figure out what are the simplest building blocks, and then to help you understand what those are and how you can combine them yourself.
I guess it remains for me to thank Hadley. I didn't mention before, Hadley's an honorary associate professor in our department. We're very pleased with this relationship, and we hope that it lasts a very long time. Just a small token of our appreciation.
Thank you.